Sir, can I please ask a doubt, sir?
Yes, you can.
Sir, if I've given a polynomial px, let's say, that is a naught plus a1x till a n xn, sir, in that case, how to realize that polynomial as a vector, sir? I'm not able to realize how what will be the each entry value for the particular
So you
vector.
look at the coefficients of the polynomial. Those
Right, sir.
coefficients.
Only yes, sir. This means a naught a1 till a n will be just these values will
Correct.
be the okay, sir.
Correct.
Okay, sir. And sir, just one doubt from the assignment, sir, that we are
Yeah.
given. Sir, in the third question, that it asks us to show that it is a weighted norm.
Yeah.
We just need to prove all the four basic fundamental properties of the norm, right?
Correct. You have to prove those fundamental
Yes.
properties.
Thank you, sir.
Sir, today there will be a quiz, right?
Yeah.
What would be the syllabus till the last class?
Do you think this is the question you should be asking right now? That gives me a feeling that you are not going to listen to what I'm saying right now. Is that true?
No, sir. Actually, I prepared till the last class. I haven't prepared actually.
No. Last class meaning yesterday's class. No.
Yeah, yesterday's
Yeah.
class.
Yesterday's class is not part of
Oh,
syllabus.
till the
Don't-
till the orthogonal till the orthogram Schmidt, right?
Gram-Schmidt orthonormalization is not part of the class test today.
Oh,
Okay.
okay, fine.
I'm
Sir, I have
just
a question.
yeah.
So, sir, regarding if we have a set of vectors and we want to analyze the span of those vectors, then will the Gram-Schmidt orthogonalization thing actually help us in order to visualize the span? I think it should. I'll just clarify.
So what do you mean visualize the span? I'm
Uh,
sure orthonormalization will help you find an orthonormal basis for the span of that vector space.
yes. So if we can find the orthonormal basis, then it's easy to visualize the span of the
Why do
vectors.
you think it is easy to visualize with orthonormal basis?
Uh, uh, like if there is overlapping sometimes if the dot product is not zero, sometimes it becomes hard. Like it's easy to visualize e1 e2 but not something like
But even E2 is not always the orthonormal basis. Na? There can be any other orthonormal vectors. So
okay.
for example, in R2 itself, there are infinitely many pairs of orthonormal vectors. You take this vector, you take this vector. They are orthonormal.
Yeah, so
You
actually you
rotate
have,
them on the circle. So in fact,
yeah.
you take any two vectors on the circle which are orthogonal to each other, they will give you a pair of orthonormals. So there are infinitely many. So
So actually, so you gave a question in the last class where you actually asked us to tell about span of two vectors, which was 111 and 110. So I was thinking like, is there a possible method analytically which can help us to visualize that?
no, so that we will see maybe today. I don't know. So let me start with what I want to do.
Okay.
So let us start with this topic of matrices. So far what we have done is we have defined vector space, and in particular we have stick to one of the very important vector spaces that we'll use in this course throughout, which is Rn. Okay. So x in Rn, basically x is a vector and you can write that vector as a column, right? So with n entries. So basically this x, a vector, is a array. Okay, it's an array. If you want, you can call it 1D array. Okay, so it only is a list, one dimensional list. Okay, so what we are going to do, so in these vector spaces we define lots of things like norm, inner product, then what else would we do? We did linear dependence, independence. Okay, we defined something which is called as orthogonality. And then finally we did something which is called as Gram-Schmidt orthogonalization algorithm, right? So that's what we have done. So we have done basis also. So these are the things that we have done in a vector space so far, and especially all these examples were considered with respect to this particular set Rn, vector. Okay, so this was a list. So today we want to start with another object which is called as matrix. Okay, matrices is the plural. So matrix. Okay, so we want to look at matrix and we want to understand these matrices well. So these matrices you see will play a very important role. So if you want to look at it from abstract linear algebra point of view, they will form a vector space and so on and so forth. So let me just introduce what a matrix is. Then we will see why those matrices are really very important. Immediately, I will give you the reason why we want to work with matrices and how matrices and certain equations related to matrices will help us understand few things in here. Okay, linear dependence, basis, and the span question that someone was asking just before I started doing this. These things will become very clear immediately after we introduce those operations. Okay, so matrix. So basically, matrix, what is it? It's a two-dimensional list of objects. So I will not call objects for us in this course as far as we are concerned, real numbers. Okay. So the notation is R and M cross N. Okay. So the notation is very consistent with what we have been using with vectors. So Rn is same as Rn cross 1. So it is a list with n rows and 1 columns. So these are the vectors. Okay, this is something that we have already seen. And if x belongs to Rn or Rn cross 1, we wrote x with one index only, x1, x2, xn, or basically x was equal to xi, I going from 1 to n. So this was enough. Okay, so that's how with only one index we were able to tell what the vector x is. Now, when I write down Rn cross m, Rn cross m, I am really saying that I am looking at an array. I am looking at an array which has n number of rows. So how many rows? N rows and m number of columns. Okay, m columns. So the first thing here will tell rows. Second thing here will tell columns. Now you will ask me, why am I making so much of fuss about this very simple symbol Rn cross n? The reason why I am doing it is that I will, now that you understood what I am going to do, I started with a list, one dimensional list. Then I went to a list which was two-dimensional list. So list, computer scientists, you can call arrays or lists or whatever you want to do. In maths, we'll call it a matrix. And now the generalization of this is I will look at three-dimensional list, four-dimensional list. So these things are called as tensors. And eventually we want to learn about them also. So they will be R, N1 cross, N2 cross, N3 cross, NR, R dimensional or R dimensional list, whatever terminology we decide to adapt, we will adapt later. So matrices is the next step, and the third step in this generalization is tensors. So we want to learn all these things in this course. So right now let us focus on this. So I will say A belongs to Rn cross M. A belongs to Rn cross M. Then what is the notation? I will denote Aij to be the ijth entry, right? So what is this saying? Look at the ith row. So this is the ith row for me. And look at the jth column. So this is the jth column for me. And what is the element in ith row and jth column? That element is this. So this is Aij. Sometimes I will write with capital, sometimes I will write with small. Sometimes I will write like this also, depends on the situation and the type of notation I am using, right? So these are the three different notations to show that these are the entries in the matrices. So in general, A, now I will write Aij, where I and J are indices between n cross m. Okay, so I will vary 1 less than or equal to I less than or equal to m, and 1 less than or equal to j less than or equal to m. So that's the range of the indices. And now I need two indices. In vectors, I need only one index. Here I will need two indices, and those two indices will be very important for me. So this is the list. So this is what matrix is. So I will tell more about examples of matrices in the lecture that I will record and send it to you for next week to view. The examples of matrices required for AI and ML. But today I want to tell you something which is important and different. Okay, so the first thing that you have to observe is A M cross N. Okay, so I will write M cross M, it doesn't matter. Has nm number of entries basically, nm number of entries. And one of the interesting operations that you have already done on these matrices. Okay, there seems to be a very big lag today. You are not able to see what I am writing, correct?
Yes, sir.
No.
Yes, sir. Not able to.
Now it has come. So there is a big lag, I think, in what. Okay, so probably today for some time you have to bear with me. So A is this matrix, it has nm number of entries. One of the interesting things that you have already done with this matrix is, for example, you had the image matrix. So I hope you all have at least had a chance to see the video lecture provided by Sumanta, the tutorial lecture where you are taught how to use this MNIST data, right? So this image matrix for the MNIST data was 28 by 28. So there you had n is equal to 28, n is equal to 28 in the notation that we are using here. So it is called a square matrix. Okay, so this matrix is called a square matrix. If n is greater than m, then it is called a tall matrix. Okay, for obvious reasons. And n less than m, it is called as wide matrix. Okay. So all these three shapes of the matrices are really very important, and they will come at different types of applications for us in AI. So this is about notations, and one operation you have already learned. What is the operation? So what did you do? You have this matrix A. So you look at the first column, then you look at the second column, then you look at the third column, and so on and so forth. And what did you do? You constructed a vector out of A by stacking these columns one below the other, right? So first you stack the first column, then you go to the second column, then you go to the third column, and so on and so forth, right? And you construct a vector which is a vector in Rnm, and this is a matrix in Rn cross m. So there is a straight away one-to-one correspondence between these two vector spaces. What is the one-to-one correspondence between these two vector spaces? So these are the two different vector spaces you are looking at, Rn cross m and Rnm. Okay, and now what you are saying? You are saying that you can identify every element in Rnm as a n cross n matrix. So every nm length vector, you can view it as a n cross n matrix. On the other hand, every n cross m matrix can be viewed as a nm vector, right? So there is a one-to-one correspondence. So that one-to-one correspondence is really very helpful. So what we will say is that these two spaces are almost same. Okay, I'm using the word almost because there are few things that we want to look at. So these two spaces you are identifying with each other. So sometimes matrices, I will like to convert them into vectors. Matrices will be converted to vectors, and I will call this operation vectorization operation. Okay, so the operation of going from Rnm to Rn cross m to Rnm. This operation is called as vectorization operation. Okay. A very useful operation, and this operation we will use very extensively when we introduce tensors. We will use this operation very extensively, but you already have seen this operation. You already have used this operation in one of your assignment problems already. So I just want to bring it to your notice that the matrices can be viewed as vectors. Okay, so if you convert a matrix into vector, then everything that we did on a vector space you can do on the matrix. There is no problem about it. But matrices themselves have a very interesting property. Okay, matrices themselves have a very interesting property, and that property is something that we are going to investigate. Okay, so that interesting property of matrices is what will give you another very interesting structure, and that structure is what we will really exploit in applications such as principal component analysis. Okay, so let's try to understand all those things. Okay, so I hope up to this part everything is clear. So now what I want to do is the following. So okay, so before this, what I will do is I will just formally define once what is matrix addition. So the operations on matrices I will just introduce. So suppose A and B are two matrices in Rn cross M. So the sizes of the matrices should be same. So if the sizes are same, then you can add the matrices. So matrix addition, C is equal to A plus B. So how do I define C? Where Cij is Aij plus Bij for 1 less equal I less equal N, 1 less equal J less equal N. Okay, so that's how you define matrix addition. And scalar multiplication, for any scalar alpha in R and matrix A in Rn cross M, alpha into A is scalar multiplication, and what is the ijth element? Alpha into Aij. Correct? That's how the scalar multiplication is defined. So these are the two operations, and it is very easy to check. What is easy to check? Rn cross M is a real vector space. What does that mean? It is a vector space over the field of real numbers. So this is a real vector space, and with what operations? With matrix addition that we have defined here and scalar multiplication. Okay, so these are the things that are really very important. So Rn cross M is a real vector space. So can you see that this is a real vector space? All the axioms, do you remember those axioms of certain set being a vector space? The axioms had to do with addition, vector addition, and vector scalar multiplication, right? So you have to go through all those axioms. One of the important axioms in addition is that there exists an additive identity. So here zero matrix in Rn cross M is an additive identity, right? Or the zero element. Or the zero vector, so to speak, in this vector space. So this is a zero matrix. Okay. So again, I will not distinguish between zero matrix, zero vector, and zero scalar in writing. From the context, you have to make sure that you understand what I am really speaking of. Similarly, for -1 belonging to R, -1 into A, the scalar multiplication, I will denote it as -A, So basically minus A is you take negative of every entry. So this is additive inverse, correct? So this guy is additive inverse. So what does that mean? A minus A is equal to 0. That's what it means. So minus A is an additive inverse of A. So these are the important observations in this vector space. These are the important observations in this vector space. Now, you look at this particular thing. Uh, I look at this R2 cross 3, okay? So this is a real vector space, we have already seen. So how are the typical matrices going to look? The typical matrices are going to look as A11, A12, A13, A21, A22, A23. 2 rows and 3 columns, correct? 2 rows and 3 columns. So this is how a typical matrix in a R23 set, R23 space looks like. Okay. So consider these guys E1, which is equal to 1 0 0 0 0 0. E2, which is equal to 0 1 0 0 0 0. E3 to be equal to 0 0 1 0 0 0. E4. Okay, so in order to say few things later, I will save myself and I'll use the notation that I really want to use. So I'll say E11, E12, E13, E21 is 0 0 0 1 0 0. E22 and E23 0 0 0 0 0 1. Okay, so these are the 6 matrices that I have written. So what can you think about this collection E11? So the first question I want to ask is that suppose I call this collection set B, then is span of B equal to R2 by 3?
Yes, sir.
And is B linearly independent?
Sir,
Yes, sir.
both are yes.
Huh?
Both are yes.
Both are yes. So how will you actually prove these things? So can you give me an outline of the proof? How to do this?
Sir,
So
we will
first give me the argument for linear
beta 1,
independence.
beta 1 2, beta 1 3 and add them all up and equate that to 0, and we will show that for it to be actually 0, all the betas have to be 0.
Correct, absolutely. So what you have to do, you have to start with the linear combination of vectors and equate it to 0. So what is the linear combination? So I will choose scalars. So beta 11 E11 plus beta 12 E12 plus beta 13 E13 plus beta 21 E21 beta 22 E22 plus beta 23 E23 is equal to 0. So this is a 0 matrix of size 2 by 3, correct? So I hope you understand that. This is a 0 matrix of size 2 by 3. And you do this matrix scalar multiplication, what do you get? You get that beta 11, beta 12, beta 13, beta 21, beta 22, beta 23 is equal to 0 0 0 0 0 0, which means that all the beta is has to be equal to 0, because now the comparison between the matrices, two matrices will be equal if they are component wise equal, right? Because if two entities are equal, A is equal to B, then A minus B equal to 0. So if A minus B is equal to 0, in this case A minus B is a 0 matrix, right? 0 matrix of the set 2 by 3. So these two things are equal. That means that all the beta i's have to be equal to 0. And the same logic you can apply to show that they will span the entire space R23. So what is the dimension of this real vector space?
R2 into
6.
3.
What is the dimension of this vector space?
6.
6.
Dimension is 6. Why do you say that? Can there
Six
be
independent vectors.
6
Huh?
independent.
There are
Six
6
independent vectors.
number of entries.
There can be no 7 vectors which are linearly independent.
Correct. There can be no 7 vectors which are linearly independent in this particular case. Absolutely right. So how will you prove that?
We can take one beta 7 into some like one more a linear combination corresponding of 7 vectors and 7 scalars, and we can show that the 7th one is dependent on the other 6 vectors. We can actually represent it using the
So you
other
can actually write that proof down.
yes.
What
I
you are
guess.
saying, can you actually write it down? Please
Yes.
give it a try. So what Satyajit is suggesting is that you take any vector y, that means you take any matrix y in this space R23, and then you show that when you add that vector y, any arbitrary vector y to this collection B, then that set becomes linearly dependent set. Okay, so what he is saying is consider this collection E11, E12, E13, E21, E22, E23, and Y. Okay, where Y in R2 by 3 is any arbitrary matrix. Okay, then what Satyajit is suggesting is that show that this set is linearly independent. Show that this set is linearly dependent. So how will you show that this set is linearly dependent?
So we will take some arbitrary 7 vectors, and then what we will do
No,
is
not
like,
arbitrary 7 vectors. Now you have taken these 7 vectors. No.
yeah, then sir, if we have taken these 7 vectors, we will actually show that like since E11 to E12 to E13, these are the basis vectors, so we can actually represent Y with that.
So
So what
no,
we'll do
how
is
can you see? That's the point I wanted to make. So good that you are making this mistake. So who told you that E11, E12, E13, E21, E22, E23 are bases? They will form a basis. Who told you that? You just showed that they are linearly independent.
We already showed that the
You have not
span of
proved
P
that
equal
they span
to
the entire space. You have not
we,
proved that they span entire space. We did not solve this problem. No?
okay.
So either you show that the span of B is R23 and then this set is linearly independent, then it will be a basis. But you have not shown that the span is entire R3. So basically showing that this set is linearly dependent is equivalent to showing that they will span the entire space R23. So that is something that you have to show. You cannot assume a priori that it is a basis and hence 7 vectors. You have to prove that this is a basis. So you'll have to do one extra step. So please show that they span R2 by 3. If you don't want to show that they span R2 by 3, then consider this set and show that it is a linearly dependent set. That is exactly same as saying that the set B actually spans R2 by 3. Okay, so once you show that, then you will be able to show that this set is a basis. And once this set is a basis, then for any R n cross M arbitrary, I can define the collection B of all matrices Eij. And how I define Eij? Eij has so Eij is the matrix. Okay, so Eij is the matrix whose ijth entry is 1 if I is equal to L and J is equal to K is equal to 0 otherwise, correct? And what is the range for the indices? The range for the indices is I and L will be between 1 to n, and J and K will be 1 to n. So I hope you understand this notation. The way I have defined these EIJ matrices, I hope you understand this notation. Pay attention, it is not a difficult thing, but this is something that you should know, because if you do not understand this, you will not understand the notations that I will use, the indices that I will work with in the tensors. Okay, so the things will get even more complicated.
Sir, can you repeat once again, because there was
You
a
read the
huge
box,
lag.
you read the highlighted box and you see if you can make sense out of what I have written. You first give it a try. I am saying that this is important. You make sure that you understand. So please give it a try. Read it. So this is the matrix, right? Eij is the matrix. So this Eij matrix you can consider it as any matrix P. So you want to define what is matrix P, you have to tell all the entries of the matrix P. What is the size of matrix P? Size of matrix P is n and n. Correct? So you replace P by Eij, then you understand what I am really saying. So this is direct generalization. This thing is direct generalization of the idea that we had used. Eij is equal to 1 if I is equal to j is equal to 0, otherwise that is I is not equal to j. That's how we defined unit vectors in Rn. You had no difficulty in understanding this notation at that time. Is that right? And what was the size, what was the length of the indices? The indices 1 less than or equal to Ij less than or equal to n. That's what we had done, right? So this is how we defined unit vectors in Rn. The same way I am defining something which is called as unit matrices or canonical matrices in Rn cross M. Does that make sense now? Comparing what we had done for vectors, same thing I am doing for matrices. Does that make sense?
Yes, sir.
Okay, excellent. So far we have done things which are exactly same like what we had done for vectors. So we are treating matrices as vectors only. Okay, and we are doing exact same things that we had done for vectors. Now comes an interesting part. I can actually define an operation between matrix and a vector. That is something that is interesting. So far what we have done, we have defined matrix addition and matrix scalar multiplication. So these are the operations that we have defined. These operations were exactly same as vector addition and vector scalar multiplication, right? So like a vector space structure, so matrices will also form a vector space. But now the interplay between the two things, interplay between the matrices and vectors, that is something that is going to be really very interesting. Okay, so the first important operation. Okay, so before that I will just introduce couple more matrices. So in a vector space Rn cross n over R. So this is the vector space. All the matrices are of the size n by n. All of them are square matrices. So what we will look at here is important matrix. I will denote by In. Sometimes I will denote it by In by n. Sometimes I will just say I. All the diagonal entries are 1. Okay. And all the non-diagonal entries are 0. So that's what we mean by. So that's what we mean by an identity matrix. Okay, so It's an n by n matrix. And this is how you define it, right? So I.
But writing IN may not be precise, right? Because M can vary. Oh, yeah, I didn't. This is about n cross n. Okay, okay. So
It's an n cross n matrix, yeah. So ijth entry is 1 if I is equal to j, is equal to 0 if I is not equal to j, and 1 less than or equal to I and j less than or equal to 1. Right? That's how I define without writing the list. Right? This is the formula for the list. Ij. Right? So this is the identity matrix, a very important matrix. Okay, so this matrix will play a very crucial role. And now I define matrix vector multiplication. I will define matrix vector multiplication. And how do I define it? I define it in a very simple way. Let A belong to n cross m and vector B belongs to m. Okay, m cross 1 or just m. This is what I have. A is in Rn cross n and B is in Rn. I want to define the matrix vector multiplication. Okay, so define matrix vector multiplication. So what will I do? I have this matrix. So first I will explain pictorially. So I denote it as AB. Okay, I denote it as AB. Generally there is no cross symbol or anything dot put between the vectors. I just write two matrices, a matrix and the vector just one besides that. Okay, so AB. And this multiplication actually is a vector which belongs to Rn. Okay, so this is something that you have to look at. So the matrix is Rn cross m. So this m is sitting here and this n is actually going here. Okay, so that's what is really happening. And this is matrix A and this is vector B. Okay, so this is B and this is A. And how do I define this multiplication of AB? So this is how I define the multiplication of AB. So suppose these are the rows of AB. Okay, so this is the first row, second row, third row, so on and so forth. And this is the column, right? So this is the column B. Then what is the first entry? The first entry is actually the inner product of this row, first row with this vector. That's the first entry. What is the second entry? The second entry is, okay, maybe I can use different colors if I have. So this is second row, and this is third row, and so on and so forth. So the second row, second entry is this guy times this guy, right? Inner product. And last, this guy times this guy. Correct? So all of these are scalars, right? So this is a scalar. This is another scalar. This is another scalar. How am I getting these scalars? These scalars are being obtained by inner product or the dot product. And what is the dot product I am taking? The dot product I am taking is the rows of A with the vector B. I can take that. Can I take this inner product? I can take this inner product. Why can I take this inner product? The reason why I can take this inner product is the row of A. The row of A. If I denote the row of A as A1 transpose. Second row of A as A2 transpose. A3 transpose. That's how I denote the rows. then A1 transpose B is the valid operation? Yes, it's the valid operation because A1 transpose contains M entries. So A1 is actually an M vector, and I am taking transpose of that M vector. I am putting that as a first row, right? So A1 is a column vector, and I am putting that column vector as a transpose the first row of A. A2 transpose the second row of A. A3 transpose the third row of A. And I am taking inner products, A1 transpose B, A2 transpose B, A3 transpose B, and so on and so forth. And those inner products I am putting here. So now you see why you need this matching condition. This M should be matched with this M. Why do you need that? Because the rows of A are the vectors transposed whose inner product you are taking with B in order to compute the product AB. Do you understand what we are doing? So if you want to see once again, so this is A, this is A1 transpose, this is A2 transpose, so on and so forth. And how many rows are there? There are n rows, so there are n row vectors that we are looking at. Then this is the matrix B, and what do we get as product of AB? The first entry is A1 transpose B, second entry is A2 transpose B, the last entry is AM transpose B. So we are looking at n inner products, right? So M cross M, M cross 1, N cross 1, this is AB. So if I want to define it in terms of lists, how will I define it? AB ith entry is actually AI transpose B for I is equal to 1, 2 up to N. And what are AI transpose? AI transpose ith row of matrix. I hope you understand what I have done here. Is there any question about what I have done here?
Yes, sir. Sir, just one question. Is that, sir, in the matrix, why aren't we considering each columns as the vectors rather than the fact that we're considering each row as a transpose? So, like, shouldn't we consider like each column and then transpose that?
No. What I have done is that I can look at the rows of the matrix or columns of the matrix. When I consider columns of the matrix, I have different understanding of what I am doing. When I consider rows of matrix, I have different understanding of what I am doing. So I am defining vector matrix vector multiplication. Is this understood or not?
Yes, sir.
I will consider columns also little later.
Okay, sir. Okay, thank you, sir.
But the notation that I am using here, is it clear or not? That's what
Yes,
I
sir.
want.
Yes, sir.
Notation is clear?
Yes, sir.
Yeah. Does it match with your previous understanding of how you used to define matrix vector multiplication? Does it match with that?
Yes, sir.
Okay. So I'll come to your question little later. I will come to that.
Okay, sir. Okay. Thank you.
No, in fact, what you are saying, Atif, is very important because that is how we will understand the geometry behind system of equations. Okay, geometry behind solutions of system of equations. So that interpretation is important, but we'll come to that little later, not right now.
Understood, sir.
Is this okay? How I have defined this? Excellent. So if you understand this, then I want you to notice something. Okay, so I will fix a matrix A in R n cross n. Okay, I'll fix a matrix A in R n cross n. For any vectors x and y belonging to Rn. For any vectors x and y belonging to Rn. and a scalar alpha in R. Okay. What am I going to do? Now you can guess what am I really going to do. Right? So let us look at, so x and y are vectors in Rn. So x plus y also is a vector in Rn. Rn is a vector space after all. So I can do this vector operation. So A into x plus y. That's what I want to look at. A into x plus y. So what is A into x plus y really? So in this notation, what is this? In this notation, this really is a vector of length n, where you have first entry as A1 transpose x plus y, second entry as A2 transpose x plus y, last entry as An transpose x plus y. But now, what can you write? You can write this as A1 transpose x plus A1 transpose y, A2 transpose x plus A2 transpose y, An transpose x plus An transpose y. Why can you write this down? Why this step is okay?
Because dot product is linear.
Correct. The dot product or inner product is a linear operation. So now this I will write down in this particular way. Why can I write this? The step I just wrote, what is this step?
We wrote the matrix as addition of two matrices.
No. This step. Don't don't go too much into the future. This step, the one which I have put under brace. So from here, why can I write this part? What is this operation I have done? It's very simple question. I just want to make sure that you understand that operation. What is this operation?
Addition over two vectors.
Correct. It is addition of two vectors. This is addition of two vectors. And this I will write down as ax plus ay. And why is that? Why can I write it down as ax plus ay?
Because it's
that's the way we define matrix vector multiplication, right? So a of x plus y is equal to ax plus ay, and a of alpha x is alpha times ax. Now if I say this, I think you can verify yourself that why this property holds true.
It is also associative property of matrix, right? Like the way we have it in vectors, like it has to show commutative, associative certain properties. So the third step where you have separated out ax plus ay in a single vector, can we also define it as one of the properties that are sufficing, which is associative?
Now, which property you are talking of? Which step you are talking of? This step, the one which just I put
Yes.
red arrows.
Yes.
That is just vector addition, no? How you define vector addition? That's all.
Yeah. Okay.
I have not used any associativity or commutativity. It's just vector addition. From here to here, it's just vector addition, no? How do you add two vectors? Two vectors are added component wise. That's all I have used. Nothing more. Okay?
Okay.
Yeah. Good. So that's all I'm saying. So you have to understand. So sometimes I will ask these questions which are very basic, just to make sure that you don't forget the very basic things. Or what happens is those very basic things are inherent now, and then you don't think twice about these operations. But suddenly, if somebody asks, then you are confused. Okay, so I think that is not. We should not lose sight of those things also. So sometimes I'll ask these easy questions. So this is what it is. So now I hope you can show this property as well. You can show this property as well.
Yes, sir.
Yes. So in general, can I say this? In general, can I say this? So I can say this, that for a fixed matrix A in Rn cross M, and for any vectors xy in Rm, I can write this thing down.
Yes, sir.
Yes, so you have to understand this equality is equality of which vectors? So first of all, do you all agree that this equality is a vector equality? This equality is a vector equality. Do you all agree? Yes. So if these are the vectors that you are equaling, what is the dimension of these vectors? What is the size of these vectors?
Rn.
R?
M.
Rn. M.
Yes, sir.
N. RNA. N.
Rn. N.
Rn, correct. So this equality is for vectors in Rn. Why? Because this vector is in Rm. This is Rn cross M. So the whole vector here on the left hand side obviously is a vector in Rn, right? And Ax. So this guy is in Rm. So this guy is Rn, this guy is Rn. You are adding two vectors in Rn, so again this guy is Rn. So this is an equality of n vectors, right? So the equality is of n vectors. So what does this remind you of? What does this remind you of? Have you seen
linear functional? Linear functional.
What principle we call this?
Superposition property, sir.
Correct, superposition property. So this looks like a superposition property. But we had seen this superposition property in case of inner products, right? Or in case of linear functionals. Now we are seeing this superposition property for vectors in Rn. Do you see the difference? So this idea actually will give rise to something we are going to define in next class, linear functions. Okay, so this idea is very important, the superposition property, and how we do this. So this understanding of how A induces a superposition property in vectors in Rn is very important. So that will help us define something which is called as linear function. Okay, we have defined linear functional. Now we can define linear function with the help of this calculation. So far so good. I hope you have understood so far what we have done. If there is any doubt in what we have done today, please ask now. Is there anything that you want to ask? So one thing that you have to understand is that this superposition, though I am writing it for vectors, actually it is coming out because of the inner products that we have defined, right? How are the vectors defined? The vectors are coming through inner products only. So the superposition that we had for inner products is actually playing a role in coming up with superposition for the vectors here. So the superposition on R, which we had done for inner products, is actually being written n times for each of the components. That's what basically is happening in this superposition property. So inherently this is a superposition of inner products only. So I hope this is clear, this is understood. Any doubt on this? Anything you want to add on this?
Sir, I really didn't I really didn't understand how the matrix multiplication, that is 8 Rnm into Rm, gave you Rn. Is it because of this formula A transpose X? Because if you are thinking in that aspect, then I get it.
No, in what aspect you mean? No, I define matrix vector multiplication in this way. This is the definition.
Yes,
So what
this
is
I
the
understood.
definition of what is the definition of matrix vector multiplication you had seen?
So it says that like in general, when you have a matrix of R and M of dimension R and M, and it is multiplied by a vector of Rm,
yeah,
then you get the resulting vector as Rn.
Rn, right? So we are also getting Rn.
Okay.
See, this is Rn.
Yes. Understood. Yeah, correct. Thank you.
Yeah. I think now what you have to do is the following. So please pay attention. I will stop sharing, and maybe we can stop recording also.
Sir, just I have one doubt, sir. That
actually now I want to announce few important things for the class test, because today we are going to have a first class test. Let us first make sure that everything goes all right for the class